neutron stars. So let's get started. Play window, share screen. Okay, neutron stars. The neutron stars is everybody's second favorite topic after black holes. We'll be talking about black holes next time. And so what we'll be talking about today is a bunch of different topics. They're all about neutron stars, but they're different aspects of neutron stars. We'll be first talking about what's called radio pulsars, which was later identified as neutron stars. So when you hear the term pulsar, think neutron star. We'll be talking a little bit more in detail about what neutron stars are. There's something called an X-ray pulsar, which was discovered in the 70s, which was actually my research topic, specifically accreting neutron stars that were X-ray pulsars. Millisecond pulsars, which are very, very rapidly spinning neutron stars. Kilonova, which if any of you were paying attention in 2017, this was the big topic of 2017. The kilonova was probably the greatest, well, no, not probably, it was the greatest scientific discovery of the 21st century, and possibly even the last 2 centuries. It's just incredible. We'll talk about that briefly. And then gamma ray bursts. So if you want to know how we're going to die, one of the possibilities could be through a gamma ray burst. So remember, what is a neutron star? The neutron star is the remnant of a very large star after it's gone supernova. So in particular, neutron stars are the remnants of large stars, but not too large, because if they're too large, the remnant is going to be a black hole, and we'll talk about that next time. A neutron star is the remnant of a 8 to 25 solar mass star that goes supernova, in actually in more detail, a core collapse type 2 supernova, and produces this remnant there. And remember, there's 3 types of stellar corpses. There's white dwarfs, which all low mass stars eventually turn into white dwarfs. There's neutron stars, which are the end game for 8 to 25-ish solar mass stars that go supernova. And remember, when you're getting up into the 8 to 25 solar mass, there's not a lot of them. The vast majority of stars in the universe, in our galaxy, are a solar mass or below. So we think there's billions of white dwarfs. There's millions of neutron stars. And then when we're talking about solar mass black holes, there's only a few million. But a neutron star weighs as much as the sun, and it's the size of Raleigh, okay? So on the scale here, here's the sun, there's the Earth, there's a white dwarf about the size of the Earth, and a neutron star has the same mass as the entire sun, actually a little more than that. And on this scale, you wouldn't even see it was a pinprick, okay? So the amount of mass that's put in that area is just beyond belief. And as I said last time, a teaspoon of white dwarf matter, degenerate matter, weighs about an elephant, and a teaspoon of neutron star matter, which is just neutrons, weighs about what Mount Everest weighs. Okay. So before we talk about the details of white dwarfs, we should talk about how we know that they exist. We know they exist because of an observation made in 1967. The woman pictured there, her name at the time was Jocelyn Bell. She was a graduate student. And she noticed that when she pointed a radio telescope at a particular star, it produced very regular and rapid pulses, okay? And this really made no sense. And the pulses were extremely rapid and extremely regular. This was a problem because nothing can travel faster than the speed of light. And if you try, and our sun, for example, our sun is a few light seconds across. And if you tried to spin our sun several times a second, it would fly apart. If you tried to pulse our star several times a second, it couldn't, because it's too large. It's several light seconds across, and since information cannot travel from one side of the sun to the other side in less than a few seconds, you can't coordinate the whole star oscillating several times a second. It just can't happen. And so when we saw something that was oscillating several times a second, we knew it couldn't be a normal star that's rotating very fast because it would blow apart. We knew it couldn't be a normal star that was oscillating, increasing and decreasing its brightness because it was going too fast. And so there was only two things it could be. It could be something very small and very bright that was rotating very fast. But at the time in 1967, we had no clue what that could possibly be. Or it was what's known as LGMs. LGM is not on the slide. This will be on your next exam 3. LGM stood for little green men. And for months, people assumed that this was an interstellar signal. This happens in astrophysics like every few months. There's a signal that somebody says is an alien. Tabby's star was the latest. There was the interstellar comet before that. The word to the wise in astrophysics, it's never aliens. And it wasn't aliens in this case either. No object can pulse so quickly. And it was Jocelyn Bell who identified this as a neutron star. Neutron star was a theoretical concept that people like J. Robert Oppenheimer and others had conceived of back in the 1930s, but nobody thought it could really exist. Does anybody know what J. Robert Oppenheimer is also famous for? Yeah, that's right. He was the scientific director of the Manhattan Project, and he built the bomb. And so this was the greatest scientific discovery of the 20th century up until that point. There were other greater ones later on. And what she said was that this rapidly pulsing neutron star, it could pulse that fast because it was really small, as you could see with those previous slides. It was incredibly tiny. And the reason it pulsed was that it was what we call the lighthouse effect, that parts of the neutron star were really bright and it would swing by us. And what was really bright was the magnetic field holding where particles would stream into the magnetic field, produce radio waves, and those radio waves would increase and decrease as the poles of those magnetic fields spun by us, as you'll see there. Okay. So what you see in this graphic is the poles of the magnetic field on the neutron star. And we'll talk a little bit more about the magnetic field. The magnetic field on neutron stars are incredibly strong. Like the field on the Earth is about half a Gauss. The field on a neutron star is 10 to the 14th Gauss, and 1 followed by 14 zero. So a magnetic field stronger than anything that we can conceive of or create on the Earth. This was one of the greatest discoveries, scientific discoveries ever. Oh, by the way, you need to hear this. What you're about to hear are those radio wave pulses being converted into sound. And this is taken directly off of the data stream, off the tapes of the radio telescopes. There's a nice beat. Got a nice beat, you can dance to it. So that's like about 1 a second. So this thing that weighs as much as the sun and is the size of Raleigh is spinning about once a second. Okay. Here's the Vela pulsar spinning about 11 times a second. Here's the Crab pulsar. Now, the Crab pulsar, I told you that neutron stars are the end game for supernova explosions. We actually know when the Crab pulsar star blew up. It was in 1054. And here's a millisecond pulsar spinning at 174 times a second. Imagine something weighing the mass of the sun, which is 1,000,000 times the mass of the Earth, something the size of Raleigh spinning 174 times, not a minute, but a second. And then the last one is the fastest pulsar ever known. This was such an incredible discovery that the Nobel Prize was awarded to Jocelyn Bell's advisor, Anthony Hewish, and another random astronomer called Sir Martin Ryle. Here's the thing about the Nobel Prize. The Nobel Prize can be awarded to up to 3 people at any one year. In 1974, they awarded it to 2. They could have awarded it to her, but they didn't. And whether they didn't award it to her because she was a graduate student or they didn't award it to her because she was a female, well, make your guess. Now, Miss Bell she's Jocelyn Bell Burnell. She's head of the Royal Astronomical Society, and she's a delightful person. I haven't met her, but my good friend is good friends with her, and they said she's just wonderful. But it's just, Nobel Prizes sometimes made big mistakes. Why did the advisor get the Nobel Prize and not the graduate student? Alex, that's a real good question. We're not in a, anyway, don't get me started. So that was radio pulsars. That was the discovery that neutron stars actually exist. Okay. And neutron stars are such extreme animals that it took a long time for people to really believe that they do exist. They're the most extreme physical objects. Black holes are even more extreme, but they're not really there. Okay. So how are neutron stars created? As I mentioned before, a type 1 supernova is a carbon detonation supernova. That's where the entire white dwarf reaches 600 million degrees simultaneously, which means all of the carbon ignites, which means there's nothing left over. However, with a type 2 supernova, much more complicated. There's a lot of implosions and explosions and neutrinos. And basically what happens is the core of the star during the supernova explosion has such a great increase in pressure and density that all of a sudden the protons and electrons decide that they want to hide together and they combine and form a neutron. And so all of the atoms that were flying around that consists of neutrons and protons and electrons, they all turn into neutrons. And so what you're left with is a couple of times a solar mass just in neutrons. And what you do is you create a nucleus that has 10 to the 54 neutrons in it, forming this incredibly dense ball. It's the densest material that can ever exist. It's basically nuclear density. And they're, as we said, very, very small. Here's a picture of a neutron star over Manhattan. If the neutron star was actually over Manhattan, the lifetime of the Earth would be measured in nanoseconds. The Earth would be completely sucked in. So hope that doesn't ever happen. So how does a neutron star exist? It exists because of what we call degeneracy pressure we talked about before. Degeneracy pressure is kind of a tough subject even for physicists. I don't fully understand it, but this is what I can tell you about it. Electron degeneracy pressure is where 2 electrons don't like to be in the same place at the same time, just like people don't like to be in the same place at the same time. And when electrons try and be in the same place at the same time, you'll have one electron that will increase its energy so it doesn't have to be at the same place in the same time. And that increase in energy is called electron degeneracy pressure. And that's what a white dwarf is. A white dwarf is degenerate matter, where the pressure is supported not by temperature, but the pressure is supported, what is resisting gravity is the electrons trying to keep away from each other. And so degenerate matter is very dense, but it's not the densest matter known. Neutron degeneracy pressure is, remember, the protons and electrons have been combined, so all that's left is neutrons. And now it's the neutrons that are trying to stay out of each other's way. But that is beyond dense. That is so dense, as we said, 1 teaspoon weighs as much as Mount Everest. Okay. And so it's much, much, much smaller and much, much more dense. And here's the thing. As you take a star that's rotating, so Lydia, is astronomy still a mainly male-dominated field? Physics has about, in terms of tenured physics professors, it's about 7% female, which is one of the worst in the technical fields. Astronomy is a little better. I think astronomy is like 20%, but still there's a lot of work that needs to be done. And it's really kind of a travesty. So, but going back to neutron stars, you all remember my my other life as a ballerina, as a ballet dancer, okay? And a ballet dancer is sitting there spinning, and as the ballet dancer or an ice skater spins, and they bring themselves in, they're going to spin faster and faster, okay? So if you're rotating around, and if we were in class physically, we could do this in person where you're sitting on a stool and you bring in your arms, you suddenly rotate a lot faster. And that's called conservation of angular momentum. Same thing happens with the star. The star is this huge, monstrous thing. It's spinning, our star is spinning about once a month. But as you shrink the size of the sun and do nothing else, to maintain the same angular momentum, the star has to spin faster and faster, just like the ballerina. As she brings in her arms, she spins faster and faster. And because the neutron star is so incredibly small, that's one of the reasons why it spins so fast. So when a neutron star is born after the explosion, it's going to spin, 20, 30 times a second. Also, as the neutron star, as the star collapses, it starts with a magnetic field that's reasonable, but again, because it's collapsing, it compresses all of that magnetic field. And so you start with a magnetic field that's a few Gauss, and you end up with a magnetic field that's 10 to the 14th Gauss. So those are just mechanical aspects of that collapse from something that's really huge to something that is mind-blowingly small. That the rotation, the angular momentum has to stay the same, so it has to spin fast. The magnetic field has to stay the same. And so if you compress it, the magnetic field of the surface goes up to 10 to the 14th Gauss. Okay. And so this is what the neutron star kind of looks like. You will not be quizzed on what is inside the neutron star because it's all guesstimates. The reason why it's guesstimates is that there's nothing that we can do on the Earth that can emulate or anything approaching these neutron star densities. And not only that, we're not fully confident in our theories of the universe for these incredibly dense objects in incredibly dense areas. So ironic that he talks about Brand on Ice. Yeah, that would be really funny. If any of you have ever seen Fantasia, you think of the hippos doing a dance. Picture right now. Do you know what color neutron stars are? Yeah, that's an interesting question. Remember that everything is thermal. And so neutron stars that are radio pulsars, they're emitting in radio waves. And so you wouldn't be able to see them visually. You would only see them in terms of the radio waves that they generate, because the core of the neutron star is relatively cold. Okay. Oh, another aspect of it is we see a lot of neutron stars that tend to be moving very, very fast. And we think that's because you've got cases where you have supernova explosions in binary star systems, and the neutron star just gets kicked out at extremely high speed. So neutron stars are by far the most extreme objects that we know of in the physical objects in the universe, ignoring black holes for now. Here's the thing about that rotation, though. So I said that neutron stars are born at about 30 times a second. As they emit these radio pulses, they're generating energy, and that generation of energy, sucks energy out of the neutron star, and that energy comes from its rotation. So a neutron star over time will slow down, just like a ballerina will slow down because of friction. A neutron star slows down because of the friction of the magnetic field generating all those radio pulses. And so in some sense, we can measure the age of a neutron star by measuring how fast it's rotating. If it's rotating slowly, it's old. If it's rotating fast, it's young. And we can quantify that because we know how old some of these neutron stars are. So for instance, the Crab pulsar, We know that was born in 1054. I forget the name of it, but we've seen supernova explosions in 1576, 1604. We found the neutron stars for those, and we can measure their speeds, and it pretty much follows that. The older they are, the slower they spin. Okay. Well, that's mostly true, but there's exceptions to that. And that we're going to be talking about X-ray pulsars and millisecond pulsars now, which are even more extreme than radio pulsars. An X-ray pulsar is like a radio pulsar, except it pulses not in radio waves, but in X-rays. Let me repeat that. It pulses in X-rays. X-rays are those things that you have to worry about when you go to the dentist's office, or the electromagnetic radiation is going to drill a hole through you. I mean, X-rays are incredibly energetic, and this thing is pulsing in X-rays. Not only is it just pulsing in X-rays, so Rebecca, yes, they will stop spinning eventually, over millions or billions of years. But here's the thing: these X-ray pulsars, which again was my research topic, are pulsing at 1,000,000 times a solar luminosity in X-rays alone. And they're pulsing in 1,000,000 times a solar luminosity in X-rays from something the size of Raleigh. This is just, I mean, it's just beyond comprehension how incredibly energetic and how incredibly bizarre these things are. Okay. And that's the average. There's at least one that is 1,000,000. Okay. And where does the energy come from? Because we've got it can't come from the magnetic field, because the magnetic field creates radio pulsars. How can you produce X-rays? You produce X-rays by stuff hitting the surface. The stuff hitting the surface is being sucked from a companion. So just like I said, most stars live in binary systems or multiple systems. Most stars are married. Here, you've got a neutron star that's got a companion. And the question is, why, when that star went supernova, did the companion not get blown up? We're not completely sure. Or perhaps the neutron star got captured. One way or another, we've observed, I think, up to 400 X-ray pulsars. So one way or another, you've got a neutron star that's orbiting a companion star, and it's sucking it dry. It's pulling off material from that companion. When that material hits the surface of a neutron star, it's moving at 30% at the speed of light. So let me give you an example. I take this pin, okay? Now, unfortunately, you can't see it because I'm going to drop it. And I dropped it on the surface of the table. You heard sound. You heard sound because what happened was this pin started at 0, it sped up, hit the surface of the table, and when it hit the surface of the table, it produced energy, which you heard as sound. Okay, so it's converted gravitational potential energy from here to here into sound, and you get a a fraction of a joule of energy out from this conversion. Okay, if you take this pen and drop it from outer space, you're going to see a fireball as it streaks through, and then it hits, and you're going to hear a loudish explosion. And it'll be in the order of, a few tens of joules. It would be very powerful. If I take this pin, and if this pin was plutonium and I blew it up in a thermonuclear bomb, this pin could generate, say, a few kilotons. So it would take out most of Durham, that would be that. If you drop this pin onto the surface of a neutron star, when it hits, it will produce 100 million tons explosion. 100 million tons. In other words, by far the most energetic thing I can do with this pin is to drop it on the surface of a neutron star. So that's why these stars can produce such an incredible flux just in X-rays. And it's in X-rays because it's hitting so fast. How hard would I need to throw a pin to charge my phone? Yeah, good question. Pretty hard. What protects the Earth from X-ray pulsar beams? So Joseph will be talking about that towards the end of this lecture. And the answer is, we believe that those beams have hit the Earth in the past. And if those beams were really close, it would be the end of life on Earth. I've been saying that a lot these days. There's a lot of things that are dangerous out there. And here is the map of these X-ray pulsars in galactic coordinates. And what I want to draw your attention to is the fact that most of these are along the galactic equator. And this is proof that these X-ray pulsars are actually stars in our galaxy. They're not out in other galaxies, because if they were in other galaxies, you would see a uniform distribution. So anytime you see things mapped on a galactic coordinate system, we'll be talking about galaxies in a few lectures. If it's along this axis, we know that they're relatively close. They're a few thousand light years away. Okay. So that was X-ray pulsars. Now, remember a few minutes ago, I said that radio pulsars are born with a rotation speed of maybe 30, 40, 50 times a second. But when I played back that sound of neutron stars, you heard a couple of them that were much faster than that. One was 172 times a second, one was 600 and something times a second. That doesn't make any sense, because if you do the calculation of, the ballerina shrinking down, you take a sun and you shrink it down to the size of a neutron star, it should be born with 30, 40, 50 times a second, not 600. So how could such a thing happen? Such a thing could happen because if you're a neutron star and you're accreting, you're an X-ray pulsar, that material that hits you will spin you up, okay? And then eventually you're going to suck dry all the material from that companion star. And so the current theory, and we believe this is correct, that these millisecond pulsars, these pulsars that are spinning faster than they possibly could if they were just naked neutron stars, were spun up by companions, which they then promptly ate. And now that the companion is gone, they're naked, but they're still spinning incredibly fast. These millisecond pulsars are spinning very fast, and they're spinning very regularly. Hold on one second. And millisecond pulsars are important to the military for a very interesting reason. So the companions are essentially a battery for the pulsar. Yeah, that's correct. What does it mean when an X-ray pulsar that is turned off? An X-ray pulsar is driven by material hitting the surface from a companion. If the companion drifts away, or if the companion has been completely eaten up, then there's no more material to hit the surface of the neutron star. And so that's what it means by turned off. So the military sent up a probe called NICER, which is currently still operating on the International Space Station. I was actually at the launch of NICER a couple of years ago. And one of the things that NICER does is it observes the rotation of neutron stars. The military funded NICER. Anybody know why the military would fund an observatory that observes neutron stars, specifically millisecond pulsars? To what extent do millisecond pulsars consume their companions? Millisecond pulsars have already consumed their companions. And so how much it's consumed, whether the companion is completely gone, we're not real sure. We're still exploring that. Art, yes, that's exactly right. So the military is interested in the millisecond pulsars for a very interesting reason. If you remember, you know exactly where you are on the surface of the Earth because of GPS. Where did GPS come from? Anybody? Well, yeah, the GPS comes from satellites, but who funded those satellites? Not quite. So, Alex, what branch of the government funded the GPS satellite system? And for what purpose? That's exactly right, Taylor. The military created the GPS specifically for targeting purposes, for targeting missiles and targeting tanks and what have you. There was no intention that this would ever become available for the civilians. At the time the GPS was created, they did, because Congress demanded it, they did produce a very low resolution um, signal that only had an accuracy of a few hundred feet, in addition to their military signal, which has an accuracy, as you know, of maybe a foot. Um, but not to go too far afield, during the Gulf War, which was in 1991, the GPS satellite was partially operational. And the military really wanted to use GPS to target their airplanes and target their missiles, but they didn't have enough GPS receivers to do that. And so what the military did in 1991 is they took the civilian signal and made it as accurate as the military signal. So then they could go to what we used to be known as Radio Shack and purchase off-the-shelf civilian GPS receivers by the hundreds, by the thousands, and put them in their fighter jets. And so that was the genesis of the civilian GPS signal, and that was the genesis. And the military never turned the civilian signal back on. They left it with the full accuracy, and that has created the modern world. The problem is you can't use GPS signal in interstellar space or interplanetary space. You need some sort of timing, because the way GPS works is it does it by timing. It's a bunch of very accurate clocks, and you measure the difference in the clock times, and that tells you where you are. So where are there very accurate clocks in interplanetary space? Well, it turns out they're millisecond pulsars. And so the military is trying to use millisecond pulsars as basically a GPS network for putting out probes in outer space. So anyway, is it the Raytheon? I don't know. When are pulsars used as opposed to cesium clocks? So the cesium clocks are in the satellites themselves, and what they do is they blanket the Earth with these time signals. But the problem is, if you're on the way to Mars, there's no cesium clocks anywhere else to create this outside blanketing of interplanetary space with time signals, except if you use millisecond pulsars or X-ray pulsars. Okay, anyway, that's just an interesting aside. By the way, there's a correlation between globular clusters and these X-ray pulsars. And the reason there's a correlation is that globular clusters are incredibly dense. There's millions and millions of stars crammed into a very small region. And because they're incredibly dense, the chances of a naked neutron star running in and being captured by another normal star is pretty high. And so that's why an unusual number of these X-ray pulsars and X-ray systems are found in globular clusters, and also millisecond pulsars. Okay, so now the last topic, which is the most exciting topic of the 21st century, is what we call kilonovas. So we've talked about neutron stars that have a normal companion that they've been eating and produces X-ray pulsars. Well, what happens if the companion for the neutron star is itself a neutron star? And that's and so we'd often thought about what would happen there, and people even named it. They called it a kilonova. And so the question is, could we ever observe such a thing? Most people thought we could not. But on August 17th, 2017, we did observe a kilonova. So this kilonova was observed using gravity waves. It was observed using gamma ray telescopes, X-ray telescopes, light telescopes, and radio telescopes. It was the first time in human history that we have observed a single event with so many different modes. I mentioned gravity waves. We'll be talking about gravity waves in a future lecture when we talk about general relativity. Gravity waves is where the entire universe shakes based on an extremely energetic event. And two neutron stars colliding is an extremely energetic event. We first detected the burst with 3 gravity wave detectors called LIGO and Virgo. And LIGO and Virgo were able to identify this green region of the sky right there. And then what happened was a bunch of astronomers searched that green region looking for galaxies where something unusual was happening. And it was a race against time. And in fact, UNC had a team doing that race. The UNC team lost the race by about an hour. Otherwise, we would be famous. And what they discovered was an event that was visible in gamma rays and then X-rays and then invisible light in this galaxy that is, I forget how many, 130 million light years distant.
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that, together, collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of two neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our Sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, a gravitational wave, CHIRP, was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these two fundamentally different types of waves could have come from a single neutron-star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 full moons. Adding information from an independent gamma ray detection from the integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with the target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect a signal of this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Swope telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes over the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, the neutron-star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of a neutron-star pair before their collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events have played a formative role in shaping the world around us. These results, for the first time, confirm that neutron-star mergers create precious elements like gold and platinum, as well as a host of other heavy elements all across the periodic table. Explosions like these, through our cosmic history, have seeded the universe with the materials that later would form new stars, new planets, and beings like ourselves who look up and wonder.
So that's the thing. Up until 2017, we weren't completely sure how very massive elements such as gold were actually created, because it didn't seem that there was enough gold that would be created in supernova explosions. We now know that most of the gold that we have, well, actually, this is not gold, but imagine that is gold. Oh, I seem to have lost myself. Hold on. That it's not gold, sorry, but if it was gold, that gold would have come from a neutron star merger, which we call a kilonova. It's called a kilonova because it's 1,000 times more energetic in terms of visible light than a nova is. It's not in the supernova range, so it's called a kilonova. And it's where the two neutron stars collide, and when they collide, some of the energy of that collision is converted directly into the shaking of the universe. There's these gravitational waves, which we'll be talking about in more detail in a future lecture. During that collision, the universe, about 3 solar masses of the two neutron stars are converted. I'm sorry, not 3 solar masses, about a solar mass of those two neutron stars are converted into the shaking of the universe. And that energy of the shaking is more energetic than all of the stars and all of the galaxies throughout the entire observable universe at that time. It's just a mind-blowing amount of energy. So the importance of the supernova kilonova discovery, the fact that so many observatories, both in space and on the surface of the Earth, were able to quickly observe a single event. It was just an unprecedented coordination. I mean, the fact that they were able to observe this within 11 hours of the initial detection is beyond belief. It tells us how big the universe is, and we'll talk about that in future lectures. It tells us about what we call the neutron star equation of state, how 10 to the 54 neutrons behave when they're together, because we have no way of simulating that on Earth. It's just too dense and too energetic. And that density, the way that those neutron stars interact with each other, tells us fundamental things about the universe itself, and tells us fundamental things about the particles that make up the universe in a way that we have no other way of exploring. It tells us how many of the heavy elements were created in the universe that seed and create those elements that are on the planet Earth and other planets. And it's also an exploration of general relativity, the way that energy is converted into gravity waves. And we haven't talked about gamma ray bursts, and now we will. There is another mystery that's been happening over the last 50 years, and these were gamma ray bursts. And these were very energetic, very brief bursts of not visible light, not radio waves, not even X-rays, but gamma rays, incredibly energetic, that would happen over very, very short amounts of time. There were two theories for these gamma ray bursts. We'll get into that in a minute. Here is the periodic chart that you were shown in that video, and look at the merging neutron stars, which is the orange. Look at the number of elements that we now believe were mostly created with neutron star mergers. I mean, this is, and the fact that we didn't know this for a fact until 2017. Astrophysics is one of the most dynamic scientific fields now. I mean, the way I teach this course now is different than the way I would have taught the course 3 years ago. I'd like to, so Joseph says, I'd like to imagine the real sound that plays in deep space when a kilonova occurs. So I will play you that sound when we talk about gravity waves. So let's get back to gamma ray bursts. First of all, I'll tell you how gamma ray bursts were discovered, and then I'll talk about the theories of gamma ray bursts. So we had sent up what's known as Vela satellites, looking for signatures of nuclear explosions from rogue states. At the time, the rogue states would be Israel and South Africa. Well, now, of course, the rogue states would be like North Korea. And the reason we used a satellite to do that was that a nuclear explosion has a double burst of gamma rays that are very distinctive for those explosions. This was a secret satellite, but this secret satellite discovered something really weird. And what they discovered was they saw these bursts of gamma rays, but they weren't coming from the surface of the Earth. They were coming from outer space, and nobody expected that. And it released the same energy as the sun, released in seconds the same amount of energy that the sun generates in billions of years. It was just a mind-blowing amount of energy. And there were two models for this. One is what they call a hypernova. It's a supernova on steroids, basically. And the other model was neutron star collisions. We now know, this slide comes from your textbook. When they were talking about these are two possible theories, we now know for a fact that both theories are correct. That we know for a fact that the source of what we call short gamma ray bursts are neutron star mergers, because we have now observed them. And we know for a fact that what we call long gamma ray bursts are the results of what they call a hypernova, because now we have observed them. Again, this shows how incredibly dynamic the field of astrophysics is. And David, yeah, I'll send you the link to those videos. And here's the map of those gamma ray bursts. And unlike the map of the X-ray pulsars, which were along the galactic equator, showing that most of the gamma ray bursts, most of the X-ray pulsars were in our galaxy, these are uniformly scattered. And what this told us was the gamma ray bursts were not coming from our galaxy. They were coming from all over the universe. And because we were able to detect them, that meant that they were incredibly energetic, both types. Okay. So these gamma ray bursts are the results of either these hypernovas or these neutron star mergers, and they produce this incredibly energetic burst of gamma rays. So a gamma ray burst like January 23rd, 1999, if it was within even a few thousand light years of our sun, it would be the end of everything. Okay. Gamma rays of doom. Now, that said, there is nothing that's even remotely possible within a few thousand light years of Earth that could cause a gamma ray burst. But again, it's interesting to imagine that you're an alien intelligent civilization that's living around a planet that does have such a star near it, that does have a couple of neutron stars that will eventually collide, that does have a star that's about to go hypernova, and knowing that your civilization has an expiration date that's pretty close. Now, all of these horrible things I've been talking about, for the most part, these are theoretical. There's no star that can go supernova within 50 light years of us. There's no proposed system that could possibly create a gamma ray burst that's within a few thousand light years of us. But, we're possibly not the only civilization out there. Okay. So that's it for neutron stars. Neutron stars are incredibly explosive, as they say. So let's do some questions. Some examples of which type of 9-star exhibit rapid pulses, which were originally suspected to be communications with extraterrestrials. Okay. And you got that right. Oops. What type of stellar remnant, sorry, I have to type these all individually, involves a rapidly rotating ball of neutrons? This should be easy. Very good. That was easy. This one is a little less easy. Pulsars usually show all of the following except. So Sam asks what a hypernova is. Yes, it's a really big supernova. The thing is that when you're dealing with supernova, you're dealing with some very extreme um, uh, environment, a very extreme pressure, very extreme in terms of temperature, and very bizarre things happen. There's something called a pair creation supernova, and a hypernova is a very, very large star that goes supernova, but some really weird stuff happens. And I'm not an expert on hypernovas, but yeah, it's basically an unusual and very energetic form of supernova. Okay. So here's the thing: a neutron star and a white dwarf, actually for black hole for that matter, none of these are truly stars. In that, if our definition of a star is something that has a nuclear fusion happening at its core, none of them are stars. There's no fusion reactions going on a neutron star. There's certainly no fusion reactions on a white dwarf. And the only exception to that are nova that go off on the surface, but that doesn't happen in the core of the neutron of the white dwarf. And there's certainly no fusion reactions going on in a black hole. The lighthouse model, let's bring that up. The lighthouse model explains how that's interesting. This question was written before NICER went up, and so if this question was on an exam, I would have to give credit for 2 answers. Okay, so what it was looking for is a rotating neutron star generates an observable beam of light. However, we are thinking of using pulsars as interstellar navigation beacons. So, and I think when they wrote this article, this question, they just thought that was a hoot. It's no longer a hoot. So let's see. There's 3 or 4 of you that haven't picked a topic yet. Maybe one of you can pick hypernova. Or if you want to switch to hypernova, let me know. And yeah, this is something you're just going to have to memorize. There's a connection between millisecond pulsars and also X-ray pulsars and globular clusters, just because globular clusters are so incredibly dense. The chances of there being 2 stars that interact with each other are pretty high. Okay. 2 more questions. Okay, so the thing here is that certainly we talked about kilonovas, the collision of neutron stars, creating gamma ray bursts. Matter spiraling into a large black hole it just wouldn't create a burst on the timescale of seconds. It's a continuous output of energy. And we'll be talking about that when we talk about black holes. Variation in the magnetic fields of the pulsar, there's no way it could generate that kind of energy. And repeated nova explosions, again, we're off by a factor of 1,000 to 1,000,000,000 in terms of the amount of energy that these gamma ray bursts produce. So the only possible explanation for gamma ray bursts is the collision of neutron stars. Now, if they had the hypernova on here, that would be another one, but they didn't. Okay. So, and last question. In contrasting the distribution of X-ray and gamma ray bursts, we find that so Sam asked, do we know what's left after kilonova? Nothing. So there's no remnant star left after kilonova. What's left is an expanding gas, expanding ball of debris that includes all those heavy elements. It's not that dissimilar from a type 1 supernova. Where are the pulsars neutron stars on the HR diagram? They're not on it. They're not on it because they're not typically visible in invisible light, and the HR diagram is really for only visible light objects. So radio pulsars are going to be visible in radio, which is off the HR diagram, and X-ray pulsars, of course, are in X-rays, which are off the HR diagram also. Okay. So certainly it's the gamma ray bursts are far beyond our galaxy, and I showed you that map where they're spread all through, on all different directions. Gamma ray bursts are more closely associated with open rather than globular clusters. Yeah, that's not really true. They're associated with the entire universe. Open clusters are just like globular clusters, except they're opener. They're less dense. So there's really no correlation there. Okay. So let's see what hypernova has to say. Yeah. That's it. Okay, that's all I have to say. I'm open for questions. Feel free to turn on your mic. And remember, you should, if you ask questions within 5 lectures, you get full credit for class participation. Also, remember that I will have questions on the exam that I only mention verbally. In today's lecture, that's going to be the LGM. What prevents matter in a neutron star collision from forming a black hole? That's a real good question. We believe that to form a black hole, you're going to need about 3 solar masses of material for it to collapse into a black hole. And you got 2 neutron stars, and those 2 neutron stars have a mass between 1.4 and a little under 3 solar masses. And in the collisions, there's so much going on that there's just not enough matter left over to create a 3 solar mass black hole. Anyway, that's what we think. We could be wrong. Favorite color is blue. What happens to the mass captured in a neutron star in a binary system? That mass is converted into all those heavy elements and produces this big ball of expanding gas and dust. Olivia out there asking the real questions. Thank you, Matthew. I agree. LGM, yes. LGM stands for little green men. How far is the closest neutron star to us? David, that's a good question. I don't know the answer to that. I'll look that up. I'm going to guess it's a few hundred light years. Because there's several million of them in our galaxy, and a few thousand sounds about right. A few hundred. If a neutron star is the most dense, then how dense would a black hole be? Oh, I'm sorry, that was privately. So I got a question that if the neutron star is the most dense object in the universe, how dense would a black hole be? I'm speaking, I'm using words in a very precise way. Neutron stars are the most precise, densest objects in the universe. Black holes aren't objects. Black holes are rips in the fabric of space-time. And a neutron star is held up because neutrons don't like to be on top of each other. And that neutrons don't like to be held on top of each other, which we call neutron degeneracy pressure, is trying to withstand the force of gravity. And when you reach about 3 solar masses, gravity wins no matter what. And all the other forces that we know, the nuclear, weak, and strong force, electromagnetic force, cannot withstand the force of gravity. Then what happens? We don't know. All we know is the black hole produces this rip in the fabric of space-time that we cannot observe past. And so certainly something is much more dense inside the black hole, but we don't know whether it collapses to an infinitesimal mathematical point or whether it collapses to a physical object. Not only do we not know, we can never know because we can never observe inside a black hole. What's the latest LGM people are talking about? Venus. The people are saying that the atmosphere in Venus is showing signs of biological life. Yeah, I don't believe it. But that said, it's certainly worth our while to investigate. Because although the surface of Venus is literally a hellhole, I mean, 900 degrees is any definition of unsurvivable. The high atmosphere of Venus is survivable and could possibly contain life. And they say signatures of a particular chemical that can only be produced on Earth through life. That said, they only observed this chemical with a single spectral line. And so Carl Sagan had a statement, which I really love. He says, extraordinary claims require extraordinary evidence. And the claim that there's life on Venus is an extraordinary claim. And right now, we have very tenuous, only ordinary evidence. Before Venus, there was the Tabby star. Tabby star was where we thought we observed a Dyson sphere around a star, Dyson sphere being a sphere around a star that only extremely advanced civilizations could build. That turned out to be wrong. And before that was the interstellar comet, a comet that we knew came from interstellar space because of its trajectory that came into our solar system and left the solar system, just like the Arthur C. Clarke novel Rendezvous with Rama. And just like Rendezvous with Rama, one astronomer felt that he had observed an increase in the acceleration of that comet that could not have been done naturally. He was wrong. Okay. He did see an acceleration, but that acceleration was caused by venting of the comet itself. So, like I said, in astrophysics, it's never LGMs. If there is intelligent life on another planet in our solar system, what planet would be the most habitable? Mars, of course. It's interesting that both Mars and Venus we now believe were habitable by human standards at some point in their past. That Mars, we now have absolute proof that there was flowing water on the surface of Mars. But the atmosphere was then stripped off by the sun because Mars does not have a magnetic field to protect its atmosphere the way Earth does. And when that atmosphere was stripped off, the planet got cold and dead. Venus, we believe, was reasonably habitable until the carbon dioxide created a runaway greenhouse effect, which produced the hellhole, which is kind of a cautionary tale for the Earth. So maybe life existed on Venus. It certainly cannot now. And finding signs of life on the surface of Venus is going to be extremely difficult. I mean, everything would be cooked, and even getting there without having your satellite cooked is beyond belief. Whereas Mars, you can have probes that survive on the surface of Mars for decades, as we have, and it's relatively, compared to Venus, relatively easy to look for fossilized signs of previous life on Mars. What constitutes as life on another planet can be as basic as just a single cell amoeba. Yeah, so Dan, the definition of life is fraught with peril, and I've got almost an entire lecture on that we'll be covering. I think it's the last lecture of this course. We'll be covering about the definition of life and how you look for life. Briefly, we're looking for things that meet the criteria that, as a famous Supreme Court justice says, "I'll know it when I see it." Okay, is a crystal life, is a computer program life. It gets really squishy, but if it comes up and says, "Hi there, how you doing?" then we kind of say it's life. How is it that planets can orbit a pulsar without being consumed? So if you're talking about a radio pulsar, yeah, that's no problem, because radio pulsar is producing a lot of energy, but it's not so much that's going to destroy the planet. If you're talking about X-ray pulsars, I I'm not sure there is a planet that we've observed orbiting an X-ray pulsar. I think there the energetics would destroy any conceivable planet. But in fact, we have observed planets around radio pulsars. There's no way that life could happen on those, unless they have their own, nuclear power plants on the surface to keep them warm. Other questions? What exactly would happen if a gamma ray burst hit the Earth? So Blake, I posted these slides. I think I already. Let's get back to that slide. So yeah, here's what they say would happen: that it would ionize Earth's atmosphere. The gas would combine to form nitric oxides, which would eliminate the ozone layer. If we eliminate the ozone layer, then we greatly increase the amount of radiation that hits the surface of the Earth, and then that would be bad. Uh, After a month-long blast of cosmic rays, everything within 200 meters of the surface would receive a lethal dose of radiation. Yeah, that's a bad day. Again, I'm just reading this. This is from the article in Scientific Sky and Telescope from 20 years ago. So I should research that a little bit more, see how bad it would be. But it would be a bad day. But again, these are things that I don't think could actually happen on the Earth, but certainly could happen to other civilizations. I think the message I'm giving is that the universe is a dangerous place, and if you want your civilization to survive, you better be a multi-planet species. Planets orbiting radio pulsars would not speed it up. No, it just, the sizes are so different. So you remember the neutron star is about a solar mass in mass. That's about 1,000,000 times the mass of the Earth. So you're talking about something that's 1/1,000,000th the mass orbiting around, and it's not going to have any effect on its rotation speed. Just like we don't have any effect on the rotation of the sun. Are there questions? If not, I'll bid you all goodbye, and I'll see you guys on Tuesday, where we start talking about black holes, everybody's favorite subject. That'll be a lot of fun. Planets orbiting radio pulsars would not speak. Can you explain gravitational radiation? Yes, in a future lecture I will. So I know we'll be covering black hole collisions. What about neutron star black hole collisions? Sam, that's a great question. I know that we have observed at least one of those. The LIGO observers, I know a couple of them personally, have been very cagey about that observation. And so that's why I've been a little hesitant to put that in my slides. But yeah, I'll talk about it as much as I can. What happens when two black holes collide? Oh, believe me, we will be covering that in great detail. That was in 2015. I actually, when I was teaching this course in 2015, I actually streamed the that press conference of that event in 2015 live, because it was one of the most, up until 2015, that was the greatest scientific discovery of the last millennium, which we will be covering. Thank you very much. I'll see you guys next time. This has been fun. Stop share and